All right. So last time in class we were talking about kind of the nucleophilic addition of amines and ammonia, things like that, to ketones and aldehydes. So we're on number 9, which is nucleophilic addition of ammonia and amines ketones and aldehydes. And we showed an example of amines. Let's do the mechanism real quickly of how that worked. So this is, actually let's draw it this way. So an amine and an acid catalyst, like ketone or aldehyde. Oops. Reacts like this. Let's show the mechanism. We did this last time, and let's step through it real quickly. What happened initially was a ketone grabbed a proton to make an RSCC. Like that. The electrons go up onto the oxygen to make the carbocation, right? And of course that gets attacked by the nitrogen. This is all what you saw last time in class, okay? And of course now the charge on nitrogen is positive. Proton transfer. Probably going to have to skip the last little bit, but we'll get close to the end. Right? And now you have a good leaving group, so it's kind of 2 steps. Kick it off, and then lose the proton on nitrogen. Okay? So yeah, that was the mechanism for how an imine is formed. The mechanism on how an imine is formed, which we did last time in class. All right? Cool. So So section D of this part is imine-like derivatives. We actually started this part also. And we started this part also. And an example is a ketone plus hydroxylamine, reacting with an acid catalyst. And that makes sort of an imine-like derivative, right? So it's got that sort of structure, C double bond N with an OH on it. And yeah, this is called an oxime. It's called an oxime. And it just has a funny name. It's not an imine, it's an oxime. I don't test you on the mechanism, I'm sorry, the names. I don't test you on the names of like an oxime, but you need to just kind of be familiar with it. You'll see it from time to time. Hydroxylamine and oxime. And of course you make water also. And if we're doing a mechanism, it's the same mechanism. All right, so same mechanism as with naming. All right, what else do we have? Ketone or aldehyde. This is a funny structure. It's a H2N, NH2, H2N. This is an NH, so it's like nitrogen, nitrogen, and then an R group. And this is either acid or there is a base version of this. So acid or base. And essentially it's the same mechanism. To give this kind of derivative. And its difference now is this nitrogen, nitrogen. And it has a different name. It's called a hydrazone. Okay? Hydrazone. Mostly the same mechanism too. So the same mechanism to make that. All right, so we got, and I'm also drawing the reagent above the arrow now. It's not that big of a deal. So yeah, so we have a couple of these different things. We have a third one. I'll draw on the bottom now. I'm just going to draw it on the arrow also. And in this case, let's draw the product and figure out what the starting material is. So what if the product is this? So it looks like we have R, C double bond N, NH, and then this, it's like a urea type functional group on the end, NH2. Has a name, it's called a semi-carbazone. Semi-carbazone. Semi-carbazone, that's C-A-R-B-A-Z-O-N-E. It's also acid, catalyst, usually. So what's the structure of the thing that's reacting with this ketone or aldehyde? Well, of course, it's just this. Just nitrogen. It's an NH2 version of that thing. So pretty easy to draw it. It's H2N. That, and of course, we flipped it over in our case. But yeah, these are a couple of these imine-like derivatives. All right, so very nice, very nice. And it's all kind of based on what you already know about imines. Okay. Okay, so we talked about these imine-type derivatives and generally how to make imines. Let's show a use of them to do a kind of cool reaction. And this is something that would be on the exam, definitely on the exam 2 when we eventually have it. It's called number 10. And the name of this reaction is called deoxygenation. What does deoxygenation mean? Maybe loss of oxygen. So it's going to wipe off a ketone or aldehyde from a molecule. Deoxygenation of a carbonyl. Deoxygenation of a carbonyl with a Wolff-Kishna reaction. So this is a Wolff-Kishna reaction is a type of reaction that we'll learn about. And so what is it? What is this idea? So this is the basic idea. The basic idea of this is that we take a ketone. That's pretty easy. We're going to react it with something called NH2, NH2, which is also we'll add KOH. So it's KOH or sodium hydroxide, and we're not using an acid, so no acid here. So no acid there, and no acid there, and it's not involved in the mechanism. I'll show the mechanism, but you make this thing here, and okay, so. What did we call that thing? We saw this, one of these kind of derivatives. We just saw it a second ago. And it was called a hydrazone. It's called a hydrazone. I'm going to try my red marker. Let's see if that works. Hydrazone. Hopefully that's a little more visible. Yeah, hydrazone. All right. And that's basic. We just saw that kind of thing. We'll go through the mechanisms in a second, how to do this hydrazone. The big difference is we're not doing this with acid. So the mechanism is going to be slightly different. Okay, and then upon kind of continued treatment with base, something crazy happens, and you get loss of the nitrogens, and it goes away. Give N2, go away. Okay, and this is what's going to be the Wolff-Kishna reaction. N2 goes away. N2, the gas, goes away. Okay, so that's the overall Wolff-Kishna reaction is kind of like the formation of the hydrazone, and then the loss of N2, and it gives you an alkane. So it actually wiped off the ketone. That's why we call it deoxygenation. So what we're going to do is mechanism part 1 and mechanism part 2. Part 1 and part 2. Let's do those two mechanisms now. All right? Okay, so let's do the two mechanisms now. Mechanism part 1 and mechanism part 2. Mechanism part 1. So the first part is forming the hydrazone. And this is under non-acidic conditions. We don't have H+. So it's going to be just a tiny bit different, but it's mostly the same. Ketone. I'm showing equilibrium conditions, but it's not crucial that you do that. I'll show why we do equilibrium conditions in a second. But what we're going to do, there's no acid. There's no acid. So what's going to happen if it's one of the things you should know about hydrazine? This stuff's called hydrazine. A couple things to know about it. It's rocket fuel, so it's used as a fuel for rockets. It's very explosive and flammable. And hydrazine, Hydrazine. And it's also carcinogenic. It's really, you have to be very careful with it. It has a lot of health effects. But it's also an amazing nucleophile. It's an amazing nucleophile. So if I'm going to use it as a nucleophile, I'm going to circle the lone pair. And what am I going to do with this amazingly nucleophilic molecule? I'm going to attack, just directly attack. So we're not doing the funny protonation thing that we did before to make an RSCC. We're not doing that. It just attacks, okay? And what does that give us? It gives me O minus and N plus. Okay? That's what happens. All right. What do we always do after nucleophilic attack? We proton transfer. So we PT from the nitrogen to the oxygen. And I think I'm missing my oxygen proton. All right, so where's my charge? Must be somewhere. Where's the charge? It's on the oxygen. Okay. Sorry. Let's go back. I screwed up. Sorry. When I proton transferred from nitrogen to oxygen, that actually neutralizes it. So, my bad. Okay, there we go. There's that OH. There we are. All right. So we proton transfer onto oxygen. And the thing is that what's weird is oxygen is actually a bad leaving group. And we kick it off. OH is a bad leaving group here. The reason is because of the stability of the hydrazone we're making. And so this is a rare case where we're kicking off oxygen as a bad leaving group. But that's okay. This is accepted, you know. There's also water around that might hydrogen bond to the oxygen and maybe improve its leaving group ability, but its stability coming off, right? But we just draw this and accept it. Okay, so what does that do? What happens when nitrogen kicks off the oxygen? Well, now we got that, and actually under basic conditions, because we're under base KOH, remember we have KOH. So under basic conditions, this is an irreversible reaction now. So, okay? Because under basic conditions, this is a low pKa, highly acidic proton, and so the base just rips it off, and that's why it's irreversible. Okay, so yeah, so we're at the hydrazone, right? Okay, and so what we have is like a series of like reversible reactions followed by an irreversible reaction. And that kind of drives the whole process. It's like reversible, irreversible, right? And that even though everything's kind of in equilibrium, the reaction proceeds all the way to the product because of this last step, right? Let's put a star there. It's like the last step kind of forces it over to the hydrazone. Oh yeah, the name of that thing. The reagent is hydrazine, and this thing, what's it called? It's called a hydrazone. Hydrazone is kind of like this ketone derivative with hydrazine. Okay, that was part one. This is the part one mechanism. What's the part two mechanism? It's kind of like the degradation of the hydrazone to give to deoxygenate, or remove that and make N2 and give you the alkane, right? So we're going to get the alkane as part two. So let's show the part two mechanism now, which is the degradation of the hydrazone to give the alkane product. All right? So cool with mechanism of part one. Let's try part two now. Okay, so now we're continuing on with the Wolff-Kishna reaction, and we're moving on to part two, which is the kind of the degradation of the hydrazone. So let's show how this goes. Oh yeah, before I do that, let's just explain what I just showed was like if A goes to, we'll say F or some other molecule. And it's like reversible, irreversible, right? What is the overall state of this reaction? Well, it's going to go, completely to F, right? It's like reversible, irreversible. It's going to go completely to F. So it's like we have a series of steps that are reversible, and then they proceed to an irreversible final step. We just saw that with part one, and now we're going to see that with part two. All right, that idea. So let's check out part two now. Okay, I'm going to erase this part. which is just kind of a general scheme of reversibility with these reactions. Okay, so what are we showing with part 2? You got the hydrazone. It's NaOH or KOH. It's just some OH source. It's a base. And we're going to basically kick off N2. Nitrogen gas goes away. Nitrogen gas is a very stable, happy molecule. So, how does this work? Well, we got the hydrazone, and you just kind of got to just memorize the sequence of steps here. We got a strong base, so why don't we do something with our strong base? All right. I'm going to do one last little thing. All right. What are we going to do with our strong base? Well, maybe we're going to use it as a base and take off a proton. Where's the proton we're going to take off? Well, as a strong base, it's going to react with one of the amine protons, which are, they're acidic enough that they can come off. So we're just going to be a base, take off a proton, and push the electrons onto the nitrogen. And this is actually a reversible step. We're going to also, in this case, have a series of reversible steps followed by an irreversible step. Okay, so what does that give us? It gives us that. It's just an acid-base reaction, right? So we took off the proton, and now we have an NH minus. Okay. Okay, and so this next step is actually resonance. N kicks in, and the electrons drop down onto the carbon. So this is a resonance structure. It's not a RSCC. It's actually it's an anion. But the electrons drop down. And now it looks like that, but we have a charge somewhere, and that's down here. Dot negative, right? Okay. Water serves as a proton source. So the carbon with a negative charge is extremely basic. So this really wants to get rid of the C minus, the C dot negative, right? So what's it going to do? From water, which is in the mixture, what's that? Whoa, I kind of messed that up a little bit. Let's fix it. So it actually grabs it from the proton and goes on to the oxygen. So take out proton off water, and now what do we got? This is reversible too. All right, so these are reversible steps. Okay, all right? Let's keep them nice and reversible for now. So we got that. We took off a proton from water. All right? Okay, so we have this intermediate. Now it's N double bond N H. All right, so now we're going to now this is an irreversible step. Base OH minus. The base is going to do the same exact thing it did before. Because initially, it took a proton off nitrogen. Now, it's going to do the same thing. But now, when it does it, guess what happens? It kicks off N2, nitrogen. All right? We make N triple bond N, and we break off And then the carbon negative charge grabs a proton. And look at that, we're done. And why was that last step so irreversible? It's because it's forming N2, right? N2 goes away. And that N2, when it goes away, is it ever coming back? When a gas goes away, it's history, right? The N2 is gone. And now we're at our final product. So this is a really cool reaction because it has a neat mechanism. There's a little bit to the mechanism. Part 2, there's not that much craziness. It's just take off the proton initially, resonate, and make a C-, grab a proton, and then kind of do it again almost, but in a way that's irreversible. So that's kind of cool. Okay, so that's the Wolff-Kishna reaction. Let's show a couple examples of the Wolff-Kishna now. All right. This is a molecule with 2 ketones on it. Reacting with KOH. There's always a little bit of water present. Anyway, what's the product? Water is also formed in the first step. When the hydrazine attacks, it's creating water. But yeah, well, we assume there's a little water. So assuming this happens in excess, what's the product? Well, got 2 ketones initially, and you have lack of 2 ketones. See, this goes away. Okay? Another one. That's not that crazy of a molecule. It's a little bridged thing. So we draw a 6-member ring kind of in boat form underneath, and then we bridge up top and draw a couple methyls on top. It's called decamphor. You can look it up. Look up the structure. Decamphor, Wikipedia or something. Do the same exact thing. What's the product? Well, it's the same exact thing. You just wipe off the ketone. The Wolff-Kishna wipes off the ketone. Cool. Side note, is the top molecule chiral or not? We're not really addressing chirality much in organic too, but is it? Is it chiral? Yeah, of course it's chiral. There's a chiral center. Where's the chiral center? You know, there's a couple chiral centers actually. There. Those are all chiral centers. Is the product chiral? Well, it's also chiral, yeah. Star. Yeah, so it's still chiral. What about camphor? Is camphor chiral? Yep. You know, this carbon, you have a ketone on one side and a CH2 on the other. So yeah, it's chiral. What about the product? Is that product chiral or not? Is it chiral? It's not. We've wiped away the chirality. Now it's symmetric on both sides. So this is achiral. Yeah, you won't be tested on chirality in this course. It's still good to review. Is it meso? Is it achiral meso or achiral non-meso? So is it achiral meso or not? What's meso? What's meso? So meso was a type of achirality. Meso, you learned this in Organic 1. Meso, what's a meso molecule? A typical meso molecule is like this. Achiral meso, right? Why was it achiral meso? Well, you have two chiral centers and a plane of symmetry, right? So there's a plane of symmetry, it's achiral meso. Is this achiral meso or achiral non-meso? Well, in order to be meso, you need chiral centers. Are there any chiral centers? Well, that's not a chiral center because you need 4 unique things on the carbon, and there's not. So that's not a chiral center, that's not a chiral center, no chiral centers, not meso. So a review of your knowledge of chirality and achirality. Okay, so that was this is a really cool reaction, and you use the Wolff-Kishner to wipe off a ketone from a molecule. You usually just use hydrazine and KOH or NaOH, all right? Cool. All right, so we did the couple reactions just now. We did the imine derivatives, and then the Wolff-Kishner reaction, which is a deoxygenation reaction to remove a ketone. Let's keep going. We got a couple more of these type of things. Number 11 is addition of cyanide. Ketones and aldehydes, and it makes something called a cyanohydrin. Cyanohydrin formation. So what is a cyanohydrin, and what are they kind of used for organic molecules? All right, so what it is, it's very simple. It's just another nucleophilic addition to a ketone or aldehyde. So cyclohexanone ketone, we often would react it with NaCN and HCl. Okay, so you can kind of think of NaCN as kind of like a Grignard. It's kind of like CN with a MGBr on it. It's kind of like the idea of CN, MGBr, right? Na plus, CN minus almost, right? It's an ion. So it's really going to be kind of like a Grignard type of reaction. So the end result, what's the product? Yeah, it's a kind of like an alcohol with a CN on there, and this is called a cyanohydrin. A cyanohydrin. And what's the mechanism of it? It's really simple. It's just dot dot negative. This is plus. We just have the nitrile directly attack, kind of like a Grignard would attack. So we have acid around, H plus from the HCl, so that's pretty easy. And it makes a alcohol with a nitrile functional group, nitrile functional group. And that combination with the hydroxy group we call a cyanohydrin. Okay, so there's two kind of follow-up reactions that occur with these cyanohydrins that people often do. You might see it on the exam. Without a mechanism, let's not worry about mechanism right now. So the things that happen after you make a cyanohydrin, one is you can react it with a lithium aluminum hydride. With water, LiAlH4 followed by water. 2 is water, yeah. What is LiAlH4? It's a reducing agent that you know. Reduces ketones and things like that. It also reduces the nitrile, which is a triple bond N thing, carbon triple bond N. It reduces from 3 bonds to nitrogen to 1 bond to nitrogen. So it's a double reducing agent. It's going to reduce the nitrile to an amine. And as you can see, we went from 3 bonds to nitrogen to 1 bond to nitrogen. The mechanism is later, so don't worry about the mechanism. Roughly speaking, though, it's H minus. What does H minus do? Nucleophile. It kind of attacks. Something like that's going to happen. We'll get to that later in the course. Okay. The other thing that cyanohydrins are used to do is you can treat them with acid, H3O plus, and it's also late. These are both later. So, but you might still see it on the exam as just a follow-up reaction to a cyanohydrin formation. If you do an index card, you can put these on an index card. Just when I say later, I mean the mechanisms later. Okay, H3O plus is not a reducing agent. It's a hydrolytic reagent. So it's going to reduce. It's going to hydrolyze. It's going to hydrolyze this. So instead of reducing it, it's going from 3 bonds to nitrogen to 3 bonds to oxygen. 3 bonds to nitrogen to 3 bonds to oxygen. What's the final functional group going to be? If you go from 3 bonds to nitrogen to 3 bonds to oxygen, it makes a carboxylic acid. And so the product is a hydroxycarboxylic acid. So we went to 3 bonds to nitrogen to 3 bonds to oxygen, and you make a carboxylic acid. Cool. All right. All right. So, and you can, like I said, this is kind of analogous to a Grignard. So, a Grignard, you have a carbon negatively charged thing attack a ketone. Let's just draw a Grignard just for comparison. So I'll just draw a Grignard up here. Right, it's an ethyl Grignard. Ethyl Grignard. And you can see it. I think you can see it kind of. So the ethyl Grignard attacks the ketone. Right? You make O minus, and then we have a step where you protonate the O minus and make the product. So you know Grignards, that's a Grignard. You can try to see the correspondence between cyanohydrin formation and a Grignard addition to a ketone. All right, great. Okay, so we did the Wolff-Kishna, which is kind of a deoxygenation thing. We did the cyanohydrin formation, which is sort of like a weird Grignard to make a nitrile cyanohydrin. Let's do number 12 now, which is addition of a phosphorus Illud. Addition of a phosphorus Illud, which is we'll explain what that is in a second. This is another this is a unique reaction. This is very different than everything else you've seen. This is called the Wittig. The Wittig reaction, W-I-T-T-I-G reaction. It's pronounced Wittig with a V. Wittig. Like V-I-T-T-I-G. It's spelled Wittig, but you don't say Wittig. You say Wittig. Okay? All right, so the basic idea of this guy, the basic idea of this reaction is this. The basic idea is this. You got a ketone or aldehyde. You got a ketone or aldehyde. You're going to react it with something. And the something is a little bit of a structure we have to draw. So it's R minus, or it's R prime P pH3. Okay. PPH3. What's pH? pH is phenyl, it's the benzene. We're not drawing that. P, of course, is phosphorus, right? So what you got now, though, is a dot negative there and a plus charge phosphorus there. So you have a separation of charge. You have a negatively charged thing, you have a positively charged thing. This is called a phosphorus illud. Phosphorus illud is Y-L-I-D-E. Y-L-I-D-E. So what is an illud? Illud, Y-L-I-D-E. It's a molecule with a separated charge like that. You have a negative charge and a positive charge. Okay? It's got a nice resonance form. Of course, what's the resonance form? It's pretty easy to see. I can kick the electrons down like this. And now you can see what the resonance form is. P. Yeah, the resonance structures, right? That's the phosphorus illud. It's got two resonance forms, right? And the net result, so when I say the basic idea of this reaction is, it just makes an alkene. It makes an alkene like that. So the alkene is kind of right there. And you can kind of see how they line up, right? I have my ketone and I have this thing. I'll draw this again in a bit, but you can kind of just, like if I drew this molecule right on top of this one, I could see how they all just kind of come together and you make an alkene. That's a good way to draw this. Okay, so we'll have to do the mechanism. It's not that bad. What's this used for? It works to make kind of like monosubstituted, disubstituted, trisubstituted alkenes. It makes out, this is a trisubstituted alkene because you have three things on the alkene. 1, 2, 3, right? It's just, you can't really use it to make tetrasubstituted. Not tetrasubstituted. You can't like do it and have it in a way that makes it tetrasubstituted alkene. But this kind of trisubstituted alkene, yeah, that works really well. Let's go through the mechanism now. It's pretty easy though. There's a little weirdness, but it's doable. We also got to show how you make the illud. Like how do you make this weird phosphorus thing? Well, that's very easy. Let's show how you make the illud, and then we'll show a couple more examples. And then I'll do the mechanism for how the alkene is formed, which is also doable. Okay, so we cool. This is the Wittig reaction. Wittig reaction. All right. So we got the basic idea down now, yeah. All right. Got the basic idea. Let's show how you make the illud. Okay, it's really easy. You start, so if I have this guy and I want to make it into an illud, a 2-carbon bromide, for example, you treat it with PPH3 PPH3, lone pair. One thing you should know about PPH3 and phosphorus with three things on it is it's a good nucleophile. So good nuke. Good nuke. It's a good nuke. And as a good nuke, it's going to do an SN2 reaction. So what's the good nuke going to do in an SN2 manner? It's going to attack and kick off the Br. Okay? So what do you got now? You got 2 carbons and a positively charged phosphorus. 2 carbons and a positively charged phosphorus. And to make the Illud, all you got to do now is hit it with a strong base. We use butyllithium. Butyllithium, 4 carbons and lithium. It's a super, super, super base. We also call it N-bu lithium. N-bu lithium. N-butyl lithium. What's the N mean? The N means 4 carbons in a row. It's not like a tert-butyl or something like that. N-butyl lithium. And as a super base, what's this thing going to do? It's going to rip off a proton. And that's the proton it rips off. So I just have it rip off the proton and give me my Illud. So that's the Illud. And again, the Illud has 2 resonance structures. The one that shows the charge separation, negative, positive, and a doubly bound one. All right, so we have 2 resonance structures in the Illud. Okay, let's just show another example kind of doing this and putting it all together. All right. Example. How do we make that into the Illud? How do we make this guy into the Illud? So nice bromine. I have a molecule with a bromide in it. What's the first step to make the Illud? Do the SN2 and then the base. So it's PH3, SN2. Where's my charge? Well, the phosphorus was neutral. It gave up its electrons, so it's positive. Rip off the proton with butyl lithium. We got that. Was a resonance. All right. Now I'm going to just throw in a aldehyde. Acetaldehyde. Okay. And you should be able to draw the product. So the product is going to be. Sometimes I'll redraw these two and just to kind of show what the product is. Let's do it over here. So I'm going to redraw these 2 pieces, and then you can. There's an easy way to see what the product's going to look like. So if I just do PPH3, there's my Illud, right? And I'm just going to sneak the aldehyde on top. You can kind of see how this stuff just goes away. It's not, that's not a correct mechanism, but you can see that stuff goes away, and now you can draw what the product is. It's just going to be an alkene between that carbon and that carbon, right? 2 carbons have an alkene, and you got, that's your product. So So that's the way you kind of can see the product of the Wittig reaction and the alkene that you form. Of course, there's a second product. These are stereoisomers. You see them both. We're not going to deal with that issue, the stereoisomer thing. The two different alkene stereoisomers you see. Let's not worry about that for this class. Okay? Cool. All right, so we showed kind of the Wittig reaction, and we showed the basic idea of it. We've shown a couple examples of it. Let's show the mechanism now. So let's see the mechanism of the Wittig reaction and how this works. All right, cool. So let's show another example of this. Aldehyde, got an aldehyde. This is a Illud, so being an Illud, I'm going to draw that resonance structure. That's the way to do it. And let's draw the final product. So with the aldehyde, that's the final product. So our R and R prime are kind of bounced up there. And we have the phenyl on the bottom. So it's a tri-substituted alkene. It's a tri-substituted alkene. That is the product, yeah? So how does this work? And let's remember the theme of this chapter. What's the theme of this chapter? The theme is that things add to nucleophiles add to ketones and aldehydes, right? So we have nucleophilic addition to ketones and aldehydes. So things add to ketones and aldehydes. Well, what is this carbon negative thing? Maybe it's a nucleophile. It's something that might add to a ketone or aldehyde. So let's do this kind of like the Grignard almost. The negative charged thing just attacks. Let's draw the mechanism now, right? The negative charged thing attacks and picks electrons up. So that's cool. Now you have O minus, right? And what else do we have? We have a new CC bond. We formed a CC bond. R prime. And we have a positive over here. We have a negative on the oxygen. We have a positive on the phosphorus. Not too crazy. Not too crazy, right? You can imagine that the negative sees the positive and might want to make a bond, and it does. So now I draw kind of like a bond that's going to form, and O minus donates in its electrons, and you get a bond to phosphorus. And now it just makes a four-member ring. So we have a four-member ring with, these two carbons are now attached, and we have a four-member ring. And this has a name that you don't have to memorize the name, but it does have a name. It's called a beta INE. It's called a beta-ene. Beta-ene. Some people would mispronounce it as betaine. It looks like betaine, but it's not betaine. Now this is actually very simple. To finish the reaction is just a very simple mechanism where two electrons go this way, two electrons go that way. And that forms the product. So it falls apart, it degrades. What's the byproduct? It's a phosphorus oxide. It's P double bond O, PPH3. Okay. One thing that you should know about phosphorus, well, one thing to know is, as we said before, PPH3 or PR3 is nucleophilic. They're very, very, very nucleophilic. They love to attack as nucleophiles when it's P and then three things, okay? The other thing to know is that phosphorus loves making bonds to oxygen. So this is actually a very stable thing, stable product. And that's what drives this reaction, is the formation of this super stable thing, this phosphorus oxide thing, okay? Let's, a couple more little examples. All right, so that was the mechanism. That's a mechanism. Let's, I did this before, this kind of example again. So, what's the product of this? If you line them up, it's really easy to see. And you kind of just say, well, these things go away. That's not a mechanism. But it is a useful tool to see, oh, what's the product going to be? That's the product, okay? Let's see. Let's do a little synthesis problem. Okay, so that's just an example of predicting the product. Let's try a little synthesis problem. Synthesis problem. Okay, so we have starting material, we got a product. Let's count the carbons. 1, 2, 3, 4, 5. Got 5 carbons in the starting material. Let's look over here. 1, 2, 3, 4, 5, 6, 7. So clearly we're adding 2 carbon stuff, 2 carbon piece. Also, it looks like we're making a CC bond. And it looks like we're, you know, if you think about it, like how many ways do you know to form an alkene? Form an alkene like in a CC bond forming reaction. Well, the answer is you've never seen that before except with the Wittig. The Wittig allows you to make a double bond like that. So yeah, we should be able to make a bond between 5 and 6, right? Okay. We also see a bromide. So the bromide is like, oh yeah, maybe the Wittig, we can do the PPH3 thing. So, and furthermore, you also see the ketone. And when I see a ketone on the left that's not doing anything, usually you think about protection. You're probably going to have to protect the ketone from the reactions of this. So this needs protection. Need protection, PG, protecting group. So what's the way to do that? How do we protect the ketone using this chapter's material? Well, 2 ways. You could do the ketal, or you could do the thioketal, the sulfur one. Well, let's use this one. And so this is very easy. You got to know the reagent. It's ethylene glycol, alcohol, 2 alcohols, 2 carbons, H+. That just protects. So we protect the left side ketone. Now we're just ready to do the Wittig. You know, we're adding a 2 carbon piece. So we just follow the Wittig procedure. So what's the Wittig procedure? First, make the Illud. How do you make an Illud? Well, we just learned how to do that with a triphenylphosphine, PPH3. Triphenylphosphine is the name of it. Yeah, and I'm going to skip the mechanism, but I'll just draw the 2 reagents. First triphenylphosphine, then butyllithium. All right, so now we have the Illud. And what's the 2-carbon thing that the illid reacts with? What's the 2-carbon thing that the illid reacts with? Well, it's a ketone or aldehyde, and it's this ketone or it's going to be a 2-carbon. Cannot have a 2-carbon ketone, so maybe it's a 2-carbon aldehyde. So it's that. That's the reagent. So it's a 2-carbon aldehyde or acetaldehyde. Right? And without a mechanism, kind of assume that kind of thing happens to give you the alkene. Very cool. How do you deprotect? Acetal, as we learned, is H3O. Cool, synthesis problem. What was the overall strategy? Well, figure out you need a protecting group. You got 2 functional groups, usually you protect one of them. Yeah, it's usually a trick. It's a trick to have a second functional group. And certainly as you're learning about protecting groups, you should always think of the second protecting group as a trick. It's like, how do I protect that thing? And especially since we just learned about how to protect ketones, okay? And then it's like figuring out, oh, it's the Wittig and 2-carbon thing we're attacking, and also how to go about making the illid for the Wittig, okay? All right, cool. Let's show a couple more little mini synthesis type examples. Practice. Make this with a Wittig. So we'll draw an alkene and say, like, how would we make it by Wittig? Well, this is usually pretty easy. How do I make that by Wittig? What are the 2 pieces? I'm given an alkene. It's like, how do you make it from a Wittig? Maybe start with a squiggly line, and then it's like, you need 2 pieces: the ketone aldehyde and the illid, the phosphorus thing. And so you can pick the way to do that. I'll just say, all right, well, I'll have a benzene. There's the ketone in this case, and then the illid is the PH3. Yeah. So now you can see how those 2 things attach through this sort of standard mechanism. One more. How do you make that from a Wittig? And we'll switch it this time. So there's the bond you're making. There's the illid. Where's the other piece? There's an aldehyde. And I just kind of, I picked it arbitrarily. You can go one way or the other. For now, we're just kind of, trying to understand the reaction, all right? Okay, so we got one last reaction to do for chapter 17. So this is number 13. This is oxidation of a ketone. Oxidation of a ketone, which sounds really weird. Like, how could you oxidize a ketone to a higher oxidation state? And this is the Baer-Villiger oxidation. course, what could you possibly oxidize a ketone to? Because a ketone already seems like a high oxidation state, right? Well, it actually goes to an ester, and it's kind of it's a weird reaction. It's one of these kind of weird reactions, and you learn a couple weird reactions. Not that weird, and it's kind of in the theme of this chapter, nucleophilic addition to ketones and aldehydes. This is really a ketone reaction. So we're going to oxidize this to an ester. That's weird. It's like an oxygen that's snuck in there to make an ester. Okay, so we added this oxygen. Okay, so and the reagent is HO. Is this? It's HOOCF3. You might remember this. It kind of looks like MCPBA. MCPBA. What did MCPBA do? It was alkenes to epoxides, right? So alkene to epoxide with MCPBA. What's the structure of MCPBA? It was remember that? That's MCPBA. And it's a weird kind of, looks like a carboxylic acid almost, but it has an extra OH, an extra oxygen. It's like a carboxylic acid with an extra oxygen. MCPBA, remember that? MCPBA. Well, this has the same thing, the extra oxygen. Okay, so let's show how this works mechanistically. All right, so what's the reagent? Well, this is you can consider this an acid. So yeah, we're just going to protonate the ketone with the acid. There we go. Protonate the ketone with an acid, and that makes a what? You've seen this several times in this chapter. 5 letters. It's RSCC. 4 letters. RSCC. RSCC. Right? And of course, as an RSCC, you have a plus charge down here. Okay. All right, now what do you got? The conjugate base is that. And what do you think that might do to the RSCC? RSCCs are electrophilic. This thing is nucleophilic. So it attaches. The nucleophile attaches, and what do you got now? So they attach. What does that look like? You got that. Those things are attached now, right? The nucleophile attached. Now those things are attached. Now it's kind of a weird concerted mechanism to finish it off and give you the product. Dot, 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 dot. So that's the H, right? So we're going to do a couple arrows, but this is, you've seen these kind of things before. I like to start by just swing down and grab the proton. Have the C double bond O, swing down and grab the proton, and then just keep pushing and pushing. So That goes there. Now the weird thing happens. This carbon-carbon bond, that CC bond right there, actually jumps to this oxygen, which is kind of weird. That's kind of weird. Because you have to cleave a CC bond, right? If you're going from a ketone to an ester, you got to cleave a CC bond, right? How do you do that? Well, that's how you do it. So it jumps. The carbon jumps to the oxygen, and then one more arrow. And that eventually, well, that gives the product. That actually makes the product. What's the byproduct? What's the byproduct from the peroxy carboxylic acid? What's the byproduct? Well, it would be a simple carboxylic acid. So of course it kind of makes sense that you went from a peroxy carboxylic acid to a normal, happy carboxylic acid. And that's the byproduct of that. Okay? Cool. We just have one last thing. I'm just going to show one last thing and we're done with the whole chapter. Okay, what about if you have an unsymmetrical ketone? Unsymmetrical ketone. So what does that mean? It's a ketone with two different sides. Okay, so let's see. How about this? And we do the bare-Villiger oxidation. Bracket, O bracket. There's your bare-Villiger oxidation. So the question is the oxygen going to sneak in onto the hindered side, or is it going to sneak into the non-hindered side? And think about it. You think it would go to the hindered side with like a bunch of stuff there, or go to the unhindered side with very little stuff? And the logical answer is, oh, it's going to go to the non-hindered side, right? The non-hindered side of the ketone. So it goes to the right, right? You think of the oxygen go to the right where there's less steric hindrance. And of course, you're wrong. So it actually goes... It goes to the hindered side, and it's not, the theory, the explanations for this are still confusing. I don't have a good, simple reasoning for this. It's very well established. So I don't have an explanation. It seems like it would go to the hindered, the non-hindered side, but anyway. So that's the case. And how about this molecule? So we'll do camphor again. Camphor, remember camphor? D-camphor. And do the same thing with the bare-Villiger oxidation and the trifluoro peroxy acetic acid. Trifluoro peroxy acetic acid. Trifluoro peroxy acetic acid. You don't have to know that name, but that's what it is. Trifluoroperoxy acetic acid. Where would it go? Hindered side or non-hindered? And generally speaking, it goes to the hindered side. So in this molecule, it's a 6-member ring on the bottom, right? 6-member on the bottom. So if we're adding an atom, it should maybe go to 7. And I just draw it the same way, almost. And it kind of makes that sort of cyclic ester. Cyclic ester. Okay? So generally speaking, we just say that the The Beer-Villiger oxidation puts the oxygen on the sterically hindered side. Historically speaking, history. The guy that discovered this was Johann Friedrich Wilhelm Adolf von Baer. It's a long name. Johann Friedrich Wilhelm Adolf von Baer. It was back when people had really long names. This is 1905. 1905. A long time ago. And there's also a Friedrich Baer who founded Baer Pharmaceutical Company. This is a different guy. So Baer is a kind of common German name. And anyway, we're done with chapter 17, and so I guess we'll jump into chapter 18 next. I guess on Thursday, and look at the iLearn site to understand how we're doing with the exams. Exam 2 covers all of chapter 17, and it will be later. It'll be covered later, so we're going to postpone chapter 2 until we're meeting face-to-face again. Okay? So yes, know this stuff, and understand you'll be examined on it later. And the Beer-Villiger reaction is often an extra credit problem with maybe the mechanism or something. All right? Cool. All right. Well, enjoy your weeks, maybe month of non-face-to-face teaching and learning. Hope it works out for you. Ask questions on iLearn, and if you have specific thoughts or questions, let me know. I switched to the red, which I think works a little better than the blue with my camcorder. Okay? All right, take care.